So let's review for test one. I just want to say that any of you that picked up the handouts, the packet of all the worksheets for this semester, this actually isn't in your packet. It's a new one I made up, this review for test one. I just feel like it's a more reflective review for the test. Now, having said that, I will go ahead for everybody and I will attach the additional reviews. I have 2 or 3 more just provided for you guys if you need some extra practice. All right, reviewing for test one, the different sections that we've covered. Okay, the first couple questions ask us to use factoring to solve the quadratic equations. A quick reminder that quadratic means the highest exponent is 2 right here. And when we graph a quadratic equation, it's like a little bowl-shaped figure. It's called a parabola. And we're going to study parabolas that open up or open down. In this course, we don't study parabolas that open on their sides from left to right. You may remember the parabola, the quadratic graph from section 2.5. All right, we're going to use factoring to solve the quadratic equations. The difference between problem 1 and 2 is that the a value in problem 1 is 1, but the a value in problem 2 is 10. We are committed to having to use factor by grouping for problem 2. You can use factor by grouping for any of these quadratic equations, whether a is 1 or not. So if you want to just do factor by grouping for problem 1, that's fine. But because a is 1 in problem 1, we can get right to the factored answer. So what we did was we created a factor sum chart. So we're looking for factors of a times c and reminding ourselves in number 1 that a is 1, b is negative 2, and c is negative 15. So let's find factors of negative 15, a times c, that sum to b, or the value of negative 2. And down this column, we just generate all the factors of 15. Let's ignore this negative for right now, and let's just record the factors of 15. Now, in each set of these factors, one of these factors has to be negative, so when you multiply, you get negative 15. But the sum of those two numbers have to be, I should put an S here, negative 2. So if my sum is negative, the larger of the factor has to be the negative number. And we can see in this set right here, if we were to add 3 and negative 5, we'd get negative 2. So we come over here. We don't have to do factor by group. We can go right to the multiplication problem. Don't forget your equals 0. If you do, then you're just factoring and you're not solving. All right, so then we're going to put x here, and we put plus 3 and minus 5. Of course, these can be switched, and that's fine. Okay, we factored, but we haven't solved yet. So this is where I kind of put that vertical bar there to separate the factors. So the zero product principle tells us that one of these two numbers in these parentheses has to be 0 if the product is 0. So we set each factor equal to 0. So from the factor x plus 3, I'm going to get the solution or the answer of negative 3. So one solution is x equals negative 3. And you always want to go back and check your solution in the original problem, and those will work. And then x minus 5 equals 0. Add the 5 to both sides. You can skip this step if you see that the factor x minus 5 produces the solution x equals positive 5. We'd want to plug 5 back in to make sure that it does check, and it will. All right, in problem 2, we're going to factor by grouping because a is not 1. So let's identify the other values, b and c. So b is 1, positive 1, and c is negative 3. Okay, we begin the same way we did when a was 1 in this quadratic equation. We find our factor sum chart. Factors of negative 30 that sum to positive 1. And I'm just going to generate all the factors of 30. The product has to be negative, but the sum has to be positive. So in each set of factors, the smaller number will be the negative number. Let's find the set of factors that when you add them, you get positive 1. And that would be this last set right here. All right, factor by grouping means that we keep the first term and we keep the last term, which is minus 3. but we take the middle term plus 1x and we break it up into minus 5x and plus 6x. And then minus 3. Remember, these two collect back to that 1x. Don't forget your equal 0. And we'll continue by grouping. This is a plus sign, so we don't have to worry about an adjustment to the sign here on the constant. Don't forget your equal 0. Common factor here is 5x. 5x divides out of both these terms, leaving 2x minus 1. Bring down the plus. Common factor here is 3, leaving 2x minus 1. And don't forget the equal 0. Okay, in each of these terms, we have a common factor of 2x minus 1, and that leaves us with 5x plus 3 equals 0. Okay, we're not done until we separate each of these factors and set them equal to 0. Let's see, I think I'll do it over here. So 2x minus 1 has to be the 0, or 5x plus 3 has to be the 0. Okay, so here we're going to put a little vertical bar here. Let's add the 1 to the other side. So 2x equals 1. Divide both sides by 2 to isolate x. So x equals 1/2. Over here, solving this, let's subtract a 3 from both sides. That results in 5x equals negative 3. And let's do the inverse operation, divide by 5 on both sides of the equation, and we get x equals negative 3/5. If you're more comfortable showing all those steps, then go ahead and do it. If not, if you're comfortable skipping those steps, then that's fine too. And both of these x values, when we're placed in one at a time to the original problem, will check. We usually don't have any kind of hiccups when you're checking your solutions, your proposed solutions in a quadratic equation. That's more down here, okay, with the radical equation. All right, let's look at 3. Let's look at the language. It says, solve the equation, and it is quadratic, by the square root property. Notice that when it says square root property, we won't have an x term, a linear term. So what do we do when we solve the equation by the square root property? Well, we isolate x squared, and then we bring in the square root. So let's add a 2 to both sides. And last, we'll divide by 3. X squared equals 10. I shouldn't say last, but of the inverse operations, I guess, before I square root. Okay, now let's bring in the square root. You're bringing in an even root. So the square root will undo the square power, leaving x, but remember it's an even, not odd root. 2's an even number, so we have to put absolute value around our x. Equals, then I kind of look over here. Can I simplify this? No. If I could, I would here in this step. And then when we want to remove the absolute value, we do so, but we have to make the adjustment to the square root of 10. So we have two solutions. We have x equals negative square root of 10 and x equals positive square root of 10. You can leave your answer this way, stacked, okay, or you could separate them. Okay, so just kind of a recap. So when you're solving by factoring, make sure that if the equation is not solved for 0, which both of these were, then you need to make sure that you zero out one side of the equation. Oh, cat, you scared me. On the square root property, we don't set it equal to the equation equal to 0. We actually isolate the x squared so we can bring in the square root. Cat. All right. Okay, 4, solve the equation by the quadratic formula. If you have a note card and you want to put the square root formula on that note card, that's fine, or a piece of paper, you can have the square root formula in front of you. I'm going to record it over here. Did I say the square root formula? I think the cat threw me off. The quadratic formula. So you can have a note card with the quadratic formula on it. All right, so x equals negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times whatever a's value is. So I'm going to come over here and identify a, b, and c. So a is 1, B is 7, and C is 12. And again, when using the quadratic formula to solve this quadratic equation, you do have to have one side of the equation zeroed out, just like when you're factoring up here, but not with the square root property. So let's just kind of build this quadratic formula. We have this fraction bar. I'll just start with the easiest part. 2 times A is 1, so that's just going to be 2. We lead off the numerator with the opposite of whatever B is, so -7 plus or minus square root of B squared, which is 7. You could put it in parentheses or not because it's positive. Negatives you want to be sure and put in parentheses because that's the way you want to enter it in the calculator. Minus 4 times A times C. Go ahead and bring down X equals again. So we'll have 2 here. That's the easiest part to take care of. In the numerator, -7 plus or minus. And at this point, I just go right to my calculator. And I'd look at what we call the radicand, what's underneath the radical. Okay, I don't need parentheses around my 7 because it's positive, so I won't bother with that on the calculator. So 7 raised to second power minus 4. I would not use parentheses here. I would just use the multiplication sign times 1 times 12. Well, that's a nice number. That's 1. All right, so now we want to separate this and make it 2 different X values because we have the plus minus, which suggests that we have 2 different answers. So I'll just take the first one. I'll take the -7 minus 1. That'll be the smaller, -7 minus 1. Put that over 2. So the numerator is -8 divided by 2 is -4. Okay, and I've checked that it does work. Like I said, we don't usually have hiccups with checking unless you're doing solving a radical equation. All right, and the second solution is X equals -7 plus 1, still divided by 2. And here, this numerator will be -6 divided by 2 is -3. So I have 2 solutions. All right, let's do 5. That's we want to get an answer for the radical equation, check all proposed solutions. All right, how did we solve a radical equation? Well, we square both sides. As long as you have your square root isolated, square both sides of the equation. So I kind of real quickly by inspection noticed that my square root is the only thing that's to the left of the equal sign, so I am ready to square both sides of this equation. So over here, you have to take the entire side. You don't square individually each term. You take and make it a group, and then you put the square on it. Squaring a square root undoes their inverse operations, so I'm left with X plus 1. No absolute value. The only time you're going to bring in absolute value is when you bring in the square root, not when you bring in an exponent, a power. All right, we certainly have some work to do over here, so I'm going to go ahead and expand quantity x minus 5, expand it, and then we're going to FOIL. So I'm going to go ahead and just FOIL kind of mentally and then record the answer here. So I'm going to have x squared minus 5x minus another 5x, which is minus 10x, and then the product of the last 2 terms is plus 25. All right, so we isolate the square root, square both sides. Now from here, we have a quadratic equation. Let's zero out one side of the equation and then try factoring to finish solving. So I'm going to subtract an x, but it lines up over here underneath this term, this linear term. I'm going to subtract a 1, and I'll line that subtraction of 1 underneath the constant. Okay, we should zero out this side of the equation. X squared has nothing to collect with when we look vertically. Collecting downward, we see that's a minus 11x, because that's just 1x. And then collecting downward and writing it across a row is plus 24. I'm going to just switch sides. I kind of like the quadratic equation to be on the left. It's just a personal preference. I just switched sides. Now let's factor. Notice that a is 1, so it should be an easy factor. You could do grouping on that. Okay, let's look for factors of a times c are 24 that sum to negative 11. In each set of factors, both the factors either need to be positive or negative to give us a positive 24, but because we want a sum that's negative, we want both of our factors in each set to be negative, and it looks like it's going to be negative 3 and negative 8 that's going to sum to negative 11. So coming over here, I don't have to do grouping unless you want to. I can go right to the multiplication problem. That's what factoring is. So I've got x minus 3 and quantity x minus 8. Let's set each factor equal to 0. So from x minus 3, I will have a solution, sometimes called a root, of x equals positive 3. And x minus 8, that factor, when set equal to 0, gives a solution of x equals 8. Oh, and I've got to remind myself, we have to go back and check, especially with the square root problems. All right, let's plug in 3 first, so to the original problem. So square root of 4, which is 2, but when I plug in 3 for x and subtract 5, I get negative 2. So x equals 3, after all that work, is not a solution. I would just kind of lightly cross it off so we can still kind of see that it's there. And by crossing it off, you're suggesting to somebody that I am eliminating that from one of the solutions. Let's plug in 8 to the original equation. So square root of 9 is 3, and then when x is 8, minus 5 is 3. So this is the only solution, x equals 8. All right, let's take a look at 6. It says solve the equation with rational exponents. Check all proposed solutions. Typically, we don't, these usually work out. It's these radical equations that we want to be mindful of checking our solutions. All right, how do we solve an equation with a fractional exponent? First thing is we inspect the exponent, that's a fraction, and we inspect the numerator. Since 5 is m, we just kind of let the numerator be m and the denominator be n. Since m equals 5 and m is odd, we know we're going to have one solution. We don't need the plus minus in front of our answer. If the numerator's exponent was even, then we'd have two solutions, and that's where we put the plus minus in front of the right-hand side of the equation. All right, how do we solve a rational equation? Well, we want to isolate x raised to the 5/2 power. So let's add a 55. Let's divide by 5. It's a nice number. If it wasn't, I'd just drag it down. At this point, to get x to the first power, we raise both sides of the equation to the reciprocal power. So I'm going to take this entire side and raise the left-hand side and the right-hand side to the 2/5 power. Multiplying 5/2 times its reciprocal gives 1, and that's what we want. So x equals, and again, had the numerator's exponent been even, I would have put a plus minus in front of the right-hand side of the equation. First thing I'm going to do here is see if this is a nice number. So I'm going to go to my calculator, and I'm going to raise 11 to the 2/5 power. Just make sure you put the fractional exponent in parentheses. Otherwise, you won't get the right answer. So first I'm going to see what kind of number this is. Not very nice. It's a decimal. So probably don't want that answer on my math lab. So let's see what they would want. What are some other things we can do? Well, I can convert to a radical format. So I would take the base of 11, and I'd take the numerator, and I would put that as the power on 11, 11 squared. The denominator represents the 5th root. And we put that right here as an index, is what it's called. And because I already know that 11 raised to the 2/5 is not a nice number, okay, I would keep the 5th root here. I would just on my calculator go and find 11 squared. and record what's underneath the radical called the radicand as 121. And this is the way I would enter it. You can go back and check, but typically these will work out on the rational equations. Or the equations with rational exponents. All right, 7. Let's solve an absolute value equation. Okay, so something else we have to memorize. With absolute value, we want to isolate the absolute value if it's not already by itself on one side of the equation. And it is isolated, so I don't have to move like a plus or a minus number to the other side. Second step, we want to remove the absolute value bars. When we remove the absolute value bars, that means we need to make 13 positive and negative. So I'll just go ahead and separate right away and put 4x plus 1 is either equal to negative 13 or it's equal to positive 13. So, oh joy, we have 2 problems to solve, possibly 2 solutions. We want to go back and check, though, at the end. I would check the radical equations and the absolute value equations. All right, let's solve this equation for x. So let's subtract a 1. So 4x equals negative 14. Divide by 4. X equals negative 7/2. I just reduced. I did check this already to save time. You might want to go ahead and do so too by plugging negative 7/2 back in for x and using your calculator to make sure that you do get 13. And you can real quickly plug in 3 and see that it does also check. All right, these first 7 problems, if you're looking for extra review, come from sections, I think 1.5 and 1.6. I think mostly 1.6. All right, this bottom right problem, now we're moving into chapter 2. This content comes from section 1 and chapter 2 if you're looking for, something to go back and look at. All right, it says determine whether the following relation, that's just a collection of ordered pairs, determine if this collection of ordered pairs is a function. Well, to be a function, we need no repeated x's. So by inspection, I'm looking at all the x coordinates. They come first. I don't see any repeated x's, so I'm going to say yes, this relation defines a function. If I plotted these ordered pairs on a graph, none of the points would line up vertically. Then if they did, it would fail the vertical line test and not be a function. All right, what's the domain? Well, we have just a collection of 4 ordered pairs, so my domain is actually going to just be from the roster method. I'm going to find the x coordinates, and then typically common practice, we put those in order from smallest to greatest. And we use this curly parentheses called a brace to represent that these are just, let me get this down here, negative 2, 5, 6, and 7. When we use braces like this, it just suggests that this is the roster method, that not the x's in between these recordings of these numbers are also part of the domain, just these x values. And the range are the y's. And again, common practice, go back, find all your y's, and let's put them in order from least to greatest. It's not wrong if you do that, but I'm just afraid that if you insert them not in least to greatest order on my math lab, that it might come back and tell you you're wrong, but you're not. It's just the preferred method of recording. All right, determine whether the following equations define y as a function of x. Determine whether the following equations define y as do these equations, when graphed, produce a graph that would pass the vertical line test? That's basically what it's saying. It's kind of hard to see because we don't have a graph for these equations. So we had to do a set of steps to determine if our equation does define y as a function of x. So let's do 11 and 12 first, just to get a visual back in our mind about what a function is, and then we'll go back to 9 and 10. For 11 to 12, use the vertical line test, VLT, to determine if y is a function of x. I didn't get a chance to put the graphs on here, so I'm going to make up 2 graphs here. Okay, let's say that I've got this linear function here, and then over here, well, I just said it's a function, so I gave it away. And then maybe over here I have a graph. This graph is maybe this oval-shaped figure. So the graph in 11 does pass the vertical line test, so yes, this graph represents a function. Each x only has one output, one y value. Notice over here that you would fail the vertical line test, because if you were to put a vertical line, say right there, then one x would have two different y's, two different outputs, so that's not a function. So now going back to 9 and 10, without a graph, how did we determine that these equations would result in a function or not when graphed? I think it's 2.1 maybe, or 2.2, that's the section. Well, what we did is we solved for y. Let's solve the equation for y. So over here, to get y by itself, I'm going to subtract a 6x. Taking these two terms, it's kind of common practice to put the linear term first and then plus 18 when we write it in row format. Okay, now let's divide by 3. I take this entire side and divide it by 3. These 3's will cancel. Y equals, okay, and what we can do is we can put the 3 underneath all the different terms of the numerator. I can't just choose to put 3 under 6 or 3 under 18. I'm going to do negative 6x over 3 plus 18 over 3. And you could have put 3 underneath each of these terms way back up here instead of using one fraction bar. Let me kind of clean that up. So y equals, and then right here I'd have negative 2x. 18 divided by 3 is 6. Okay, so does this equation define y as a function of x? Well, if our exponent on y is odd, then the answer is yes. If the exponent on y is even, like over here, we're probably going to say no. Another way to kind of think through this is, does this equation define y as a function of x, is choose any x value, any number for x, and see how many different answers you would get out. So like if I chose x to be 0, by plugging in x equals 0 and doing the math, I would get a y of 6. There's no way when I plug in 0 for x that I would get anything other than 6. So you choose x to be 4. If x is 4 and you did the math, you get an answer of negative 2. It'd always be negative 2. Each x only has one y. So yes, this equation defines y as a function of x. All right, let's look at 10. All right, so what do we do? Determine if the function defines y as a function of x. Okay, got to get y by itself. So let's subtract x squared to both sides of the equation. I'd put negative x squared plus 1. Doesn't matter the order. Oh, I have an even exponent. I think I want to say no, and I'm probably going to. To get y by itself, let's bring in the square root on both sides of the equation. And again, it's just one radical on both sides. So this whole group goes underneath the radical called the radicand then. All right, square rooting, I brought that in. A square means I'm going to have two solutions, so I need the absolute value because the exponent is, the root is even. And then I can't clean this up here. I can't simplify that, so I'm just going to drag it through. Now I need to remove absolute value, so I put the plus minus in front here. All right. By inspection, when I look at this equation, yeah, the exponent is 1 here. It's an odd, but then something funny is going on over here. If x is 0, let's just test. If x is 0, then I would get the square root of 1, which is 1. But if x is 0 and I get 1 here, then it's either the positive 1 or the negative 1. So if x is 0, I can either get positive 1, or if x is 0, I can get negative 1. I have repeated x's, so my answer is no. This equation does not define y as a function of x. 13, use the graph to determine the following, the function's domain. Okay, there are arrows on this. My software program just didn't do it, so I'm going to go ahead and put arrows on these graphs down here. Now this is actually, I meant this to be a point and ordered pair. The graph stops here, so there's no arrow. In 13, use the graph to determine the following. the function's domain. Domain are all the x's. This is a polynomial function, so its domain is all real numbers. Okay. This describes all the x values. Now the parentheses here aren't describing an ordered pair, they're describing a collection of x values that belong to this graph. What's the range? Start from the low y. This graph will peak out at a high y value of, let's read it from the vertical axis, 3. So let's go the smallest y, negative infinity, to 3, and I can't include the 3, so I use the bracket. If you put this in as 3 comma negative infinity, my math lab probably wouldn't take it. It's just, I think they want it in order from smallest to greatest. Do we have any x-intercepts? Well, I kind of scanned, starting from far left, moving over. Yes, I have an x-intercept here, and I have an x-intercept here. Okay, that was meant to go through -2. Your problem will be more accurate than mine, but let's just go ahead and say that the x-intercept is x equals -2, and the y-coordinate of any x-intercept is 0. We also have another x-intercept over here, and if we kind of, look at the graph, it looks like it's less than half, so I'm going to say 1/4. 1/4, and the y-coordinate is 0. So the y-coordinates are 0 for x-intercepts. Again, your graph will be more clear and more specific. It's just kind of the error I had with trying to get this to graph. Do we have any y-intercepts? So I start scanning the y-axis, start looking up. Yep, this graph crosses the y-axis at this y value of 1. So the ordered pair that represents that point is x is 0 for a y-intercept, and the y-coordinate is 1. The function values. When you're asked to find the function values from a graph, they want you to find the y values. So that suggests that these numbers are your x coordinates. So f of 0 equals, so if we know this is x, we go to x equals 0, we look up, we look down, oh, f of 0 actually has a y value of 1. And remember, this function notation can be written in this ordered pair format, so everything matches up, everything's good, we have no conflict. All right, what's f evaluated at -1? What's f evaluated at x equals -1? So we stand at the origin, we move over to x equals -1, we look up, we look down, oh, here's the graph. It appears that the output value, or the y, is 3. So another way to say this is that the ordered pair -1, 3 is a point on the graph. This is just function notation. All right, 14. Use the graph to determine the open intervals on which the function is increasing. So increasing is going to be anytime the graph's going up. Okay, decreasing anytime the graph's going down, and constant if the graph is ever flat. I don't have another color here to highlight. All right, so is the function ever increasing? Yes, it is. It increases right here. But we have to remember that these are the x intervals. So I see that the graph is increasing from 2, 0, but it goes off to infinity. It never stops increasing. So the graph of this function begins to increase at x equals 2, but continues off, as suggested by the arrow, increasing to x values way out here towards infinity. Where's the function decreasing? On what x values? Well, let's identify that piece of this graph where it's decreasing. So this ordered pair is -1, 3. That's the point, the location of this, or a point right here. And then it stops decreasing right here at x equal, or the ordered pair 2, 0. So on what intervals of x's, so from x equals -1 to x equals 2, from x equals -1 to x equals 2, remember this is not a point, it describes the x coordinates of points on the graph where the graph is falling, okay, is where this graph is decreasing. Where's the function, oh, that's an error, constant. I'll have to fix that. Okay, well, the graph is constant, flat, from x equals -5 until this x coordinate of -1. So this ordered pair right here is -5, 3. We say that the graph of this function is constant on the x values from x equals -5 to x equals -1. And to kind of quickly wrap up 15, because I'm running out of time here. Okay, what do we want to do here? Use the given graph to find each of the following. We want to find the numbers, if any, at which f has a relative maximum. What are these relative maximum? And then we want to find the minimum. Well, I can see from this graph that I don't have a high y value. I mean, the graph continues, but there's not like a relative maximum in a neighborhood where I have a high y value. So actually, we don't have any maxima. We do have this low spot right here. That's our minimum. So let's go back and make sure we understand the question. It says the numbers, if any, at which f has a relative minimum. Well, they're just suggesting for us to describe the x-coordinate, the numbers where the function has a relative minimum. So the x-coordinate would be -1. This question, the way it's worded, what are these relative minima? Now they're asking for the y-coordinate. So the y-coordinate is -3. Sometimes you're asked to give the ordered pair at which you have your relative mins and maximum, which that would be -1, -3. Just kind of watch out for the language of how you're being asked to locate the mins and maxes. Okay, we'll continue in the next video with the rest of the review.